Section 14.7, Catalysis. A catalyst is a substance that changes the speed of a chemical reaction without undergoing a permanent chemical change itself in the process. Catalysts are very common. Most reactions in the body, the atmosphere, the oceans occur with the help of catalysts. Most industrial chemical research is devoted for the search of new and more effective catalysts for reactions of commercial importance. Extensive research efforts are devoted to finding means of inhibiting or removing certain catalysts that promote undesirable reactions, such as those that corrode metals, age our bodies, and cause tooth decay. Homogeneous catalysis. A catalyst that's present in the same phase as the reacting molecules is called homogeneous catalyst. Examples around both in solution and in the gas phase. Consider, for example, the decomposition of aqueous hydrogen peroxide, H2O2, into water and oxygen. In the absence of a catalyst, this reaction occurs very slowly. Many different substances are capable of catalyzing the reaction represented by equation 1429, including the bromide ion, as shown in 1419. The bromide ion reacts with hydrogen peroxide in an acidic solution, forming aqueous bromide and water. The brown color observed in the middle photograph of figure 1419 indicates the formation of bromine. If it were a complete reaction, bromide ion would not be a catalyst because it undergoes chemical change during the reaction. However, hydrogen peroxide also reacts with the bromine generated in equation 1430. The bubbling evident in 1419b is due to the formation of oxygen. The sum of equations 1430 and 31 is just equation 1429. When hydrogen peroxide is completely decomposed, we're left with a colorless solution of bromide ion, as seen in the photograph on the right in 1419. Bromide ion, therefore, is indeed a catalyst of the reaction because it speeds up the overall reaction without itself undergoing any net change. It is added at the start of reaction, reacts, and then reforms at the end. In contrast, bromine is an intermediate because it is first formed and then it is consumed. Neither a catalyst nor the intermediate appears in the chemical equation for the overall reaction. Notice, however, that the catalyst is there at the start of the reaction, whereas an intermediate is formed during the course of the reaction. On the basis of the Arrhenius equation, equation 1419, the rate constant K is determined by the activation energy and the frequency factor. A catalyst may affect the rate of reaction by altering the value of either the activation energy or the frequency factor. The most dramatic catalytic effects come with lowering the activation energy. As a general rule, a catalyst lowers the overall activation energy for a chemical reaction. A catalyst usually lowers the overall activation energy for a reaction by providing a different mechanism for the reaction. In the decomposition of hydrogen peroxide, for example, two successive reactions of hydrogen peroxide with bromide and then with bromine take place because these two reactions together serve as a catalytic pathway for hydrogen peroxide decomposition. Both of them must have significantly lower activation energies than the uncatalyzed decomposition, as shown schematically in figure 1420. Figure 1420. Energy profiles for uncatalyzed and catalyzed reactions. The energy profiles for the uncatalyzed decomposition of hydrogen peroxide and for the reaction as catalyzed by bromide ion are compared. The catalyzed reaction involves two successive steps, each which has a lower activation energy than the uncatalyzed reaction. Notice that the energies of the reactants and products are unchanged by the catalyst. A heterogeneous catalyst exists in a different phase from the reactant molecules, usually as a solid in contact with either gaseous reactions or reactants in a liquid solution. Many industrially important reactants are catalyzed by the surfaces of solids. For example, hydrocarbon molecules are rearranged to form gasoline with the aid of what are called cracking catalysts. Heterogeneous catalysts are often composed of metals or metal oxides. Because the catalyzed reaction occurs on the surface, special methods are often used to prepare catalysts so that they have very large surface areas. The initial step in a heterogeneous catalysis is usually adsorption of the reactants. Adsorption refers to the binding of molecules to a surface, whereas absorption refers to the uptake of molecules into the interior of another substance. Adsorption occurs because the atoms or ions on the surface of the solid are extremely reactive. Unlike their counterparts in the interior of the substance, surface atoms and ions have unused bonding capacity. This unused bonding capacity may be used to bond molecules from the gas or solution phase to the surface of the solid. The reaction of hydrogen gas with ethylene gas to form ethylene gas provides example of heterogeneous catalysis. Even though the reaction is exothermic, it occurs very slowly in the absence of a catalyst. In the presence of a finely powdered metal, however, such as nickel, palladium, or platinum, the reaction occurs rather easily at room temperature. The mechanism by which the reaction occurs is diagrammed in Figure 1421. Both ethylene and hydrogen are adsorbed on the metal surface. Upon adsorption, the hydrogen-hydrogen single bond of hydrogen breaks, leaving the two hydrogen atoms that are bonded to the metal surface, as shown in Figure 1421b. The hydrogen atoms are relatively free to move about the surface. When a hydrogen encounters an adsorbed ethylene molecule, it can form a sigma bond, or to one of the carbon atoms, effectively destroying the carbon-carbon pi bond and leaving an ethyl group bonded to the surface via a metal-to-carbon sigma bond. This sigma bond is relatively weak, so when other carbon atoms also encounters the hydrogen atom, the 6 carbon-hydrogen sigma bond is readily formed and the ethylene molecule is released from the metal surface. The site is ready to adsorb another ethylene molecule and thus begin the cycle again. Enzymes. Many of the most interesting and important examples of catalysis involve reactions within living systems. The human body is characterized by an extremely complex system of interrelated chemical reactions. All of these reactions must occur at carefully controlled rates to maintain life. A large number of marvelously efficient biological catalysts are known as enzymes, are necessary for many of the reactions that occur at suitable rates. Most enzymes are large protein molecules with molecular weights ranging from 10,000 to about 1,000,000 atomic mass units. They are very selective in the reactions that they catalyze, and some are absolutely specific, operating for only one substance in only one reaction. The decomposition of hydrogen peroxide, for example, is an important biological process. Because hydrogen peroxide is strongly oxidizing, it can be physiologically harmful. For this reason, the blood and livers of mammals contain an enzyme catalase, which catalyzes the decomposition of hydrogen peroxide into water and oxygen. Figure 1423 shows the dramatic acceleration of the chemical reaction by the catalyst of beef liver. Although an enzyme is a large molecule, the reaction is catalyzed at a very specific location on the enzyme called the active site. The substance that undergoes a reaction at this site is called substrates. The lock and key model, illustrated in 1424, provides a simple explanation for the specificity of an enzyme. The substrate is pictured as fitting neatly into a special place on the enzyme, the active site, much like a specific key fits into a lock. The active site is created by coiling and folding the long protein molecule to form a space, something like a pocket, into which the substrate molecule fits. Figures 1425 shows a model of an enzyme lysozyme with and without a bond substrate molecule. The combination of an enzyme and the substrate is called an enzyme-substrate complex. Although Figure 1424 shows both the active site and its complementary substrate as having rigid shapes, the active site is often fairly flexible. Thus, the active site may change shape as it binds to the substrate. The binding between the substrate and the active site involves intermolecular forces such as dipole-dipole attractions, hydrogen bonds, and London dispersion forces. As the substrate molecules enter the active site, they are somehow activated so that they can be capable of extremely rapid reaction. This activation may result from the withdrawal or donation of electron density at a particular bond by the enzyme. In addition, in the process of fitting into the active site, the substrate molecules may be distorted and thus made more reactive. Once the reaction occurs, the products then depart, allowing another substrate molecule to enter. The activity of an enzyme is destroyed if some molecule in the solution is able to bind strongly to the active site and block the entry of the substrate. Such substances are called enzyme inhibitors. Nerve poisons and certain toxic metal ions such as lead and mercury are believed to act in this way to inhibit enzyme activity. Some other poisons act by attaching somewhere on the enzyme, therefore distorting the active site so that the substrate no longer fits. Enzymes are enormously more efficient than ordinary non-chemical catalysts. The number of individual catalyzed reactions events occurred during a particular active site, called the turnover number, is generally in the range of 1,000 to 10 to the 7 per second. Such large turnover numbers correspond to very low activation energies.